So what I'm going to tell you about today is some work we're doing with ultrasound imaging to look underneath the skin at calf muscles as they produce force, and in parallel with passive elastic ankle exoskeletons that you might be familiar already with. But I'm going to spend the first few slides telling you about the device. So this was a collaboration with Steve Collins. It went all the way back to graduate school, coffee shop discussions where we conceived of this device, which is inspired by the fact that animals and robots make good use of springs in their legs, and so why not try to attach springs outside the body, sort of like an exotendon, in parallel with the muscles to offload force and hopefully reduce metabolic energy cost. So I won't go into the details about this. You can read about it in the 2015 paper. Basically, the way it works is it's really simple. It's got a spring that lives on the back of your calf muscle in line with the musculotendons in line with the plantar flexors. And a key innovation here was that we needed a clutch to make sure that people didn't need to work against it in swing phase when they reset their foot for heel strike. The principle, though, is just that you can see here as the stiffness increases from hot to cool colors, we're able to offload more ankle joint moment by increasing the exoskeleton torque. You'll see that changes in kinematics occur, so as you get really stiff, people tend to dorsiflex less. And there's sort of a diminishing returns that you'll notice where we can't offload torque indefinitely as we increase the spring stiffness. But we could get about 25% of the ankle joint moment supported by the device. And this was the really cool result. We were able to show that compared to walking in normal shoes over here in gray, and also walking with the exoskeleton without springs, we could reduce the metabolic cost of walking by about 7%. But the trick was you had to have a spring that was of intermediate stiffness. So this is what I want to spend the rest of the talk trying to explain. Got this cool result. We weren't able to explain it entirely by mechanical measurements externally, so things like joint moments and powers. And so we had to start looking under the skin in order to figure out the mechanism. So let's think about it a little bit more. Oh, one thing that I'll also say is that device transfers no net energy to the user, right? So all it's doing, it literally is offloading force, and in fact, it's actually absorbing some energy because no spring is perfect. So we're reducing metabolic energy cost and taking energy from the person on net. So how the heck does that happen, right? So if we take a muscle level perspective and we think about what the spring's actually doing, start here, there's the exoskeleton in parallel with the muscle tendon unit, and we kind of wrench down across musculoskeletal organizational scale a bit. We think about, okay, we've got all three plantar flexors there. Those are the MTSs, or muscle tendon units. And so the exoskeleton's offloading some force, right? Because these forces have to sum to the total force or moment that you need to walk. And then if we wrench down further into a single muscle tendon unit, I'm going to talk about soleus today, you have interesting architectural things going on, like there's pennation angle and such. The forces that the fascicles that are consuming metabolic energy consume are actually not even in line with the tendon, okay? And then, to make it even more complicated, you've got connective tissues that can act when the muscle's operating at long lengths, and that little sort of heat thing there is muscle consuming metabolic energy to produce force. So that's the cross-bridgey stuff. And so if you take this perspective, you automatically think about, well, how do we quantify that heat? Obviously, we can't measure it, but let's think about some mechanical analogs. We also read back through the literature, and there are other people that don't believe that work is the best indicator of metabolic cost. So Roger Crom's crew and all the way back to C.R. Taylor in the early 90s and late 80s had this idea that it's active muscle volume that we should be paying attention to. And one way to think about that is through measurements of EMG, for example, which may be a reasonable proxy for how much muscle volume is active. So we took inspiration from this. This is a good one to read if you want to get back into that literature. Tim Griffin, Tom Roberts, and Roger Cram showed that this equation here, which says that the metabolic rate is related heavily to the active muscle volume, the estimate of active muscle volume in the lower limb during walking, and even during walking with load. So I want to try to apply that thinking to exoskeletons now. So to do that, let's focus on that little widget of a fascicle that's producing heat, and think about it in terms of a simple hill-type model, which includes force length and force velocity properties. When you do that, you write down the active component of the force. We're going to ignore passive components of the force production for now. There's good reasons for that. Most of the time during walking, the soleus muscle is on the ascending limb. So it doesn't benefit from passive contribution to begin with. So we choose to ignore that for now. You have this relationship. You can write it so that you isolate activation on the left-hand side, which we think is most related to active muscle volume. And now we're good to go. We can start to think about this now in terms of mechanism. So what I want to kind of do here is summarize this equation by saying that basically it boils down to force demand. That is how much force your muscle has to produce. The exoskeleton affects that directly, right? That's intuitive. It's offloading force. But there's this other thing that's important, which means that force is not activation. It depends on where that muscle is working on its length, tension, and force velocity curve, and we need to consider that. Intuitively, it's hard to think about what an exoskeleton does to those two things, and that's why we need ultrasound imaging. Okay? Correct, this is a very simple model that doesn't include transient things like history dependence and so forth. It's a good first step, I think, though. Okay, so let's try to go through the thought process of what happens to the force length and force velocity, and I want to focus on force length. When you put an exoskeleton in parallel with a muscle tendon unit that has a large tendon on it. This is key. Plantar flexors have a large Achilles tendon, and then there's a muscle, and I'm putting a spring in parallel with that. So our thinking went, okay, if I offload the muscle tendon unit, that means I have less force in the series elastic element in the Achilles tendon, which means it should be less stretched, right? And if I operate with similar kinematics, which tends to happen over most of the range of stiffness, that means the muscle on average must be longer. So that's a prediction that we can reduce force demand, but also we can potentially increase force capacity by improving the operating point in the length tension space of the muscle by making it longer when we put a spring in parallel with it. And you can think about that in terms of the force length curve. This is kind of the shift that we expect. This represents the force length curve at 100% or some higher level of activation, say 50% for walking. And if I put a spring in parallel, what's going to happen is this dotted line is the linearized version of the length tension curve of the tendon. The muscle has to adhere to that curve because it's coupled to it. So if I reduce the force on the muscle, its displacement should change in relation to whatever the stiffness of its series tendon is. So if I reduce force, I should not only get a reduction in activation, but also a shift in the length. So we think not only do we reduce force demand, but we also increase force capacity. And that, both of those things lead to reduced activation. Okay, so we did an experiment here. Our tethered robot is not as cool as Stanford's, but it's basically the same thing. Picture's not as pretty. But the idea is we took a motor and controller and we emulated these springs instead of attaching real springs to people to mimic the device that I showed you earlier on in the talk. And we did a full gait analysis, but we included ultrasound imaging. We think we were pretty careful about getting enough training and things, but after hearing some of the talks here, maybe people weren't fully adapted to the device, who knows. We had a training session, and then we assessed mechanics and energetics on different days. And key here was the ultrasound. This is kind of what an image that we get looks like. The yellow line is tracking a fascicle in soleus, which is deeper than the gastrocs, which are these superficial muscles that you can see. And so we calculate the fascicle length change directly from these images. Not calculate them, but make measurements of it. Okay, so here's some data. What you're going to see here is on the x-axis is the percentage stride, and y-axis this is muscle activation, just normalized to the peak value of soleus that we observed over all the trials. And so maybe not that surprisingly, soleus activation goes down with increasing stiffness. We recovered a similar metabolic cost relationship to the original study, which indicated that you can't be too stiff, right? There's a sweet spot on the stiffness metabolic cost relationship. And what was cool is that we found a reasonably strong relationship between the activation rate of the soleus and the whole body metabolic energy cost. with respect to zero stiffness springs in the exoskeleton. So this indicates that active muscle volume might actually be a thing. So let me just try to quickly explain what's going on here in terms of the fascicles. Forces went down like we expect. We also found evidence for increased fascicle lengths, which you can see here. And when you think about that on the length tension curve, this is an estimated length tension curve. We didn't measure length tension curves for our individual subjects. We just took this from literature. But you can see that we predict a rightward shift. What that means is that the amount of force per unit activation increases, right? So you have an increased force capacity and a reduced force demand, especially for low stiffnesses, which explains why the metabolic cost is lower for low stiffness. If you think about the force-velocity relationship, another interesting thing happens. So here again, forces go down. If you measure velocity of the soleus muscle, it increases. So you make muscles longer, they have to shorten faster at the end of the cycle to get back to the same spot. And that's not a good thing for force capacity. So especially for the stiffest exoskeletons, we found a reduced force per unit activation. So force demand is still going down, but the force capacity is poorer. And that, we think, partly explains the upturn in the metabolic rate, whole body metabolic rate at high stiffness. Okay, so just to finish up, we found that changes in metabolic rate were pretty highly related to changes in the muscle activation rate of the soleus only, which was pretty cool. That's one muscle. It's a big muscle, but we were able to show about 44% of the variance just by looking at activation rate of soleus. For lower stiffness, the reduced activation rates could be tied back to reduced force demand, but also improved force capacity, which is really cool. For the higher stiffnesses, the increased soleus activation rate was due to the force demand being swamped out by poor force capacity due to highly increased shortening velocity. And I want to leave you with this image. So human in the loop exoskeleton control may not only be useful for externally measured variables. It's possible that we could put muscle dynamics in the loop as well to do what I would like to do is controlled experiments to actually test the idea that moving lengths on the length tension curve can affect metabolic energy consumption. Thank you.
You first.
I think the reasoning is based on the observation, or maybe the assumption, that the kinematics do not change, and therefore also the external moment does not change, and therefore required muscle force does not change over all the conditions that you've shown. And you quickly glanced over that, but I noticed that the changes in metabolic energy consumption are subtle, and maybe also the changes in the kinematics are subtle. So how convinced are you that these external moments do not change?
The external total moments is pretty similar up until very stiff spring. So there's pretty good evidence for moment invariance. But it doesn't mean the kinematics aren't changing. They clearly are. I showed that to you. But for the springs that work well, we have direct measurements of what the fascicles are doing. So independent of that, the idea that the shift happens is true. We measured it directly. So
Sure.
It's true that my hypothesis was based on a very simple model with many assumptions, but the direct measurements support the idea. So, yep.
It's my job.
Sorry.
Super interesting talk. So at some point you started talking about activated muscle volume, but then in the end you mentioned activation rate. Do you mean the same thing, or do you actually mean the derivative in the second case?
Yeah, no, the derivative is important. I didn't have time to go through all that. So it's actually pretty unclear why that divide by t thing seems to matter, but it does. If you read different papers, there's different takes on why that is. So Art's published a lot of good stuff, and there's a classic paper by Hogan that shows when you turn muscles on and off quickly, that there's a cost to turning muscle on and off, right? Taylor, all the way back to Sierra Taylor, and then Roger Crom and many others after him, the cost of force hypothesis idea, always divides by contact time. And there are many reasons for doing that. One is it might encapsulate the force velocity penalty, because if you have longer time on the ground that needs to shorten over, you're going going to pay an activation penalty for that. It could also be inclusive of these rate-dependent on-off effects by accident. So I don't think we have the right equation yet, but it seems to be important to divide by a time.
Max?
I just wonder if you could put back up the slide while you answer other questions about the muscle activation rate definition.
The regression from the very beginning.
I'm not even sure where it was, but there's this like your conclusions are based upon muscle activation rate.
Yeah.
I'm not sure how that's defined. So is there a slide where?
I didn't carefully define it, but what we did is we integrated solely the CMG and then divided by the stance time. So it's an average of the muscle activity divided by the time over which that activity or that activation was applied by the muscle.
Thank you.
Katie?
So we'll see, and Katie from Stanford. So we see with the powered exoskeletons that we have people who are just naturally better at using the devices. Do you think that there's something at the physiology level that could explain that?
Yeah, I mean, so one idea is that if you have a really compliant Achilles tendon to begin with, then these shifts in force capacity that you see by offloading could be bigger. So that would be something to look at, is how the morphology of the underlying musculature might relate to performance. Yeah, I mean, that's my best guess from a muscle perspective. I think all these ideas we're seeing about people who are doers and psychological makeup of people also might be more, those things may actually be more important in terms of the learning. But where you get to at the end, I think, should depend on the morphology in some way.
The next speaker can set up in the meantime, and we'll take 2 more questions. Manoj?
Maybe you mentioned this, but show this correlation with activation rate. Did you track correlation with other more traditional metrics like average muscle work rate or?
Yeah, so work rate was not significant muscle level, which was surprising, but I have a table that I can show you afterward with all those regressions. This one turned out to be the best. We also split it out for different phases of the stance. It's kind of interesting. I'll share that with you offline.
Okay, and then
David, UNLV. I was just curious if there's any indication of increased muscle recruitment at more proximal joints than you or the hip with those stiffer spring.
Yeah, so we see a huge amount of TA coactivation. So I'm guessing if we added TA activation rate in there, that R squared would jump. There's also a lot of other compensations at the knee, for example, to prevent hyperextension. So that upturn is not just coming from soles.
let's
Thank
thank
you.
the speaker.